Good morning, everyone. Welcome to the EGU General Assembly. My name is Barbara Freire. I'm the EGU Media and Communications Manager, and I will be hosting 5 press conferences for you today. Our media portal is media.egu.eu, and you'll find there a series of documents and images relating to this and other press conferences that the Alfred Wegener Institute and the British Antarctic Survey have contributed. They are organizing this press conference together with the EGU. And so our first press conference today is on Beyond EPICA, the quest for a 1.5 million year ice core. And I'd like to remind you that we'll have presentations from all of the speakers, and then we'll open the floor for questions from journalists in the room, and also those watching remotely via the web stream. Taking part in this press conference, we have Olaf Eisen, who is the coordinator of Beyond EPICA Oldest Ice, Coordination and Support Action, and he's based at the Alfred Wegener Institute, Helmholtz Zentrum für Polar- und Meerforschung in Bremerhaven in Germany. Catherine Ritz, who is a Beyond EPICA Oldest Ice scientist. She's at the Institute for Geosciences and Environmental Research in Grenoble, France. Carlo Barbanti is a coordinator of Beyond EPICA Oldest Ice Core, so the next phase of the project is at the Ca' Foscari University of Venice in Italy, and the Institute for the Dynamics and Environmental Processes in Venice, Italy. And finally, we have Barbara Steny. She is a Beyond EPICA Oldest Ice Core scientist at the same university as Carlo Barbante. And I will now hand over to our speakers.
Good morning, everybody. Thanks for coming and thanks for your interest. And we are just 4 representatives of the whole consortium of 14 different institutions from 10 European nations. And for later interviews, if you're interested, there are more people from our consortium in the room. So if you're interested in a special person from some country, just get back to us and we can point out who you can talk to. So today we want to present the results of our pre-site surveys, which we conducted over the last 3 years in Antarctica, to find the best place to drill an ice core, which is 1.5 million years old. And ice cores are unique for geosciences because they are an archive of the paleo atmosphere. We know from ice cores what the atmosphere in the past looked like. The oldest ice core we have so far goes back 820,000 years. It was drilled between 1996 and 2004 at the Dome C drill site. That's the site where you also find the Concordia station. But this ice core doesn't cover the time between 900 and 1.2 million years ago, where we actually had a transition in the climate system. So here you see an image of Antarctica, a map, and we focused on 2 regions where we had pre-site surveys. The red dot here and the purple dot, that's near Concordia, the Dome C region in East Antarctica. And the other area we investigated is here around the Dome Fuji region. And after our 3-year endeavor, we decided to go for this red dot here, which is 40 kilometers away from Concordia. So why do we actually look for an ice core which goes back 900 to 1.2 million years, hopefully 1.5 million years. Here you've got an image of the temperature changes of the Earth reconstructed from paleoproxies. The lower curve is basically the kind of a temperature distribution in the Earth, and the upper curve is the carbon dioxide content of the atmosphere. And you see from 1.5 million years ago until 1.2 million years ago, glacial, interglacial phases, like warm and cold phases in the Earth system, gray and white bars here, they changed with a rhythm of around 40,000 years. From 800,000 years ago, as we know it from an ice core, the Concordia ice core, EPICA ice core, the European project for ice coring in Antarctica, at that time it changed to a rhythm which is 100,000 years long. So we have a change from 40,000 years to 100,000 years over this time period here, which is rather colored here, which we call the mid-Pleistocene transition. And to really understand what the climate system was like in this transition period, what drove this transition from 40,000 to 100,000 years, we need to know what the atmospheric composition is like. And this is actually the goal of Beyond EPICA, to drill an ice core not only back to 800,000 years as we have it, but go into this part here, hopefully all the way back to 1.5 million years ago. And with that, I hand over to Catherine Ritz, who was one of the lead scientists for the pre-site surveys in the Concordia region.
Hello. So I was coordinating the geophysical survey to select a site, the best site as possible to obtain such a record. So the criteria to find a very old age are, of course, the ice sheet has to be relatively stable in the past, or at least we expect it to have been stable, with a low regions with a low accumulation rate, because the smaller the accumulation rate of snow every year, the more years you have in each meter, and a low horizontal velocity to reduce the risk of folding of the layers. This select the central regions of East Antarctica, and in the map that Olaf showed you, you see the Dome Fuji and Dome C regions. On a more local study, we want to avoid basal melting. That's the main criterion, because basal melting removes the layers at the bottom of the ice sheet and removes the old layers, and that's why we only got 800,000 years in EPICA. It's because it is melting at the base. And basal melting depends on the thickness of the ice and the heat given by the Earth. And we also want to have a region where we can do some modeling to assess at which height above the bedrock it could be the 1.5 million years and what would be the resolution. To do so, we had to go to a very small scale. So the red dot that was on the map of Olaf is here you have Concordia Station, and here you have the region, the main region we investigated. And all the tracks, all the red lines are tracks with a ground-based radar in order to obtain data on thickness and internal layers. Because one major thing is that we can see inside the ice, we can see internal layers that are supposed to be isochrones. These layers, fortunately, the red layers you see here, so you see two examples. This one was done with airborne survey, and the other one with the ground-based radar. These layers can be dated back to 366,000 years, because we could follow the layers from the EPICA core to that place. And with a model that takes into account the fact that we know the age of these layers, we can extrapolate downward and produce, they are not very easy to see, produce simulated ages and see where could be the 1.5 million years layer. And here is the final spot where we choose the most likely site, and you see that the purple here line is something like 80 meters above the bedrock. And finally, here are the locations we choose as the most interesting places, and the proposed site that is here. It fulfills almost all the criteria. It is very close from the dome, so the horizontal velocity is something like 5 centimeters per year. It is not too thick, so it avoids basal melting, and you see there are a lot of lakes. We saw a lot of lakes around at the interface between ice and rock, so that gives us a criterion where it is melting and where it is not. And the black line is almost a safe line. Above this line, we expect that the melting shouldn't be a big problem. And it is relatively flat. The simulation gives that indeed we can have 1.5 million years with an acceptable resolution. And finally, when we had a look at the selected site, the layers seemed well stratified. Unfortunately, as you can see in the very bottom, where are the layers that we are interested in? the radar doesn't really see the layers. So we cannot be fully sure that they are well stratified, but we have many indication that it's a rather safe place. And now I let Carlo.
Thank you. Thank you. Should this one?
Yeah. Oh, another one.
Thank you very much, Catherine. EU is investing a lot of money in research on new mitigation and adaptation strategies. And of course, at the same time, there are many knowledge gaps in the climatic system that have to be fulfilled in that. And many projects are going on this respect. And certainly, Beyond EPICA is certainly one of these. And it really will become one of the iconic projects in the years to come. As Olaf said, we started to think about that at the end of the EPICA adventure about 10 years ago. So it took 10 years to conceive the project. It took more than 3 years with more than 22,000 kilometers of radar survey to find a spot where to do the drilling. And it will take the next 6 years to get an ice core back. It is a long process, as I told you, with a lot of logistic beside. I mean, it will be a light camp made in about 40 kilometers from the main station of Concordia, which is run by France and Italy together. Is a gigantic effort from a logistic point of view, where the Institut Polaire Français and the Italian National Polar Antarctic Program are running. So, as I told you, it will be a pretty light camp with about 14 person in the field, organized in shift. The time in which we can work in the field is very short. It's about 2 months per year, because the conditions are incredibly harsh. Average temperature is of about minus 52 degrees. So that means that when we arrive in the early season, the temperature is pretty chilly, minus 50. Then we can work on 2 shifts, about 16 hours per day. And then in the central part of the period, it will take 24-hour shift with 3 groups working, and with the full speed. I will come a little bit later with the planning of the seasons, as we are going to do. In the field, which is more or less as it is in the picture here, this is a project that we ran a few years ago in East Antarctica, in Talos Dome, but the camp will be more or less organized like that. And consider that all around there is nothing for thousands of kilometers, if with the exception of the Concordia station, which is our also rescue module in 40 kilometers from there. Say that, I mean, is a very challenging program. We are really looking at the ice cores, which is the only climatic record which, as Olaf mentioned, give at the same time forcing and response factors is something really exceptional. And again, from a logistic point of view, it's not easy to carry tons of material in the site. The site is located here, where you see the big star around here. There are 2 ways in which we can carry things, and there are through Mario Zucchelli, flying to Concordia, because the roadway is a bit is fully of crevasses, so it's very dangerous to transport gears through Mario Zucchelli straight to Concordia. And the other way, as you see with the modules like this, with tractors and caravans, all the material is transported from Cap Prud'homme to Dumont d'Urville and then to Concordia. It takes about 12-15 days to transport all the material. Say that this site has been selected after thousands of kilometers of radar survey. It will occupy about 5,000 man days in the field in those conditions, as I told you. A lot of transport by air freight with about 22 tons, 100 cubic meters of fuel, 80 tons transported through traverses, as we have seen. And overall, the funding supplied by the EU so far is at the beginning 2 million for the survey that we had, and we hope to conclude the grant agreement with the Commission in the next few weeks, I would say, and hopefully starting the project, the drilling project, in a few months in June. Say that, I mean, the time plan is more or less the one that I want to show you here. Is a 6-year program. The role of the IPEV and ENEA and the national programs from France and Italy is fundamental for that. And of course, this is really a step forward after the EPICA project. We plan to extend the record from 800,000 to 1.5 million years. But unfortunately, or fortunately, as you want to take it, the most exciting information we are looking at will be squeezed in the deepest part of the core. So there is not a linear relationship in between the age and the depth. So most probably the ice as old as from 800,000 years to 1.5 million years will be squeezed in the last 200 or 300 meters of ice. This implies that you have and we have to wait to get all the results at the very last season, which will be most hopefully on 23-24. On this, I mean, in the next 4 years, however, we are not resting. We are, of course, setting up the camp. As you see, we have to start drilling the deepest, down deeper and deeper with a lot of manpowers in the field. But of course, since, as I told you, the ice will have the information squeezed on a very few 100 meters, we also have to set up new analytical tools, and there would be really a great improvement from analytical point of view and also from a technological point of view. And this project is not just a dream of a bunch of crazy European scientists, but is something that comes with extraordinary efforts of an international partnership, which is called IPICS, is the International Partnership for Ice Core Sciences, and which brings together scientists from all over the world with ambitions to go and drill this deep ice core in several parts of Antarctica. As we are working in Dome Sea region, we have other colleagues, Russian colleagues aiming to retrieve an ice core in Vostok, and others in Japanese colleague in Dome Fuji, or Chinese colleague in Dome A, and I'm missing someone American. For sure. American are also trying to look at that, and Australians, which are looking forward to, which are just a couple of, or just 1 year behind us in terms of organization, which are aiming to retrieve a new ice core very close to where we are. So it's a great effort. It will be a great adventure, but certainly we have the best team that we can aim for. So let's start and we'll see where we arrive.
Okay. Good morning. Okay, so I'm just coming back to the first, to one of the first slides showing the climate records that we have in the last 1.5 million years. And so just to give you, again, some clues. So at the bottom, we have the isotopic record from the benthic, from the marine records, which is a combination of ice volume effects and deep sea temperature effects. And as you see, there is this change, has already Olaf mentioned, on between a 40 kilo year world and a 100 kilo year world in the last part of the records. And we call this part the middle Pleistocene Transition. So what we have before from the EPICA ice core, it is these temperature reconstructions from the water isotopes, and these cover the last 800,000 years. And at the same time, we have this wonderful iconic record of the carbon dioxide that is covering the same time span. So what we are lacking is the information of greenhouse gases before. There are some low resolution and not continuous information that we can obtain from the sedimentary records, and this is from the boron isotopes, but there is no a continuous record of carbon dioxide. So in order to understand this transition, we needed to have a new record to go farther back in time. And okay, so but which are the hypotheses of this change in climate cycle between a 40 kiloyear world and 100 kiloyear world? There are several hypotheses that has been put forward, and the main idea is that it became harder to deglaciate after the middle Pleistocene transition. And there are several hypotheses, as I said, and there are two main groups of hypotheses. The first one is we had a CO2 concentration decrease in the atmosphere, so there is less energy available for deglaciating. And the second is a slow change in the bedrock material underlying the northern ice sheets from a sedimentary regolith to crystalline rock. And this is changing the ice sheet area and thickness, and so it's the vulnerability of the ice sheet to orbital energy, and so to orbital forcing. So what we will obtain from this ice core is a number of measurements that we will have. First of all, the greenhouse gases, as well as their isotopic composition. We will obtain Antarctic temperature and precipitation, as well as ice sheet altitude, and also other novel proxies that has the CF4, that is a proxy of the weathering conditions, and as well as the mean ocean temperature using the noble gas thermometry. These are novel proxies that we are going to use. And in order to answer this scientific question that underline this climate transition, we really need to understand why we have this change around 900 kiloyears ago, and why do we live now in a 100 kiloyears world. So unless we understand this transition, we cannot say that we have really understand our current climate systems. Thank you.
Thank you very much for your talks. We'll now open the floor for questions from the journalists here in the room. Does anyone have any questions?
Hi, it's Adam Vaughan from New Scientist. I just wanted to pick up on the points that Olaf and Barbara were saying about the gaps of knowledge we're trying to fill in here. Can you speak? You spoke a little bit about how it'll teach us more about the past. Can you talk about how it might also shed more light on how the climate might change in the future as well?
So if understood well, if this information can help to understand the future, obviously, because we can constrain all the Earth climate systems simulation if we have more information about the climate change in different period and with different climate boundaries and how these will evolve. So we needed to know these different. Okay. Yeah, we need this. Yeah, because otherwise there are just model. Okay.
Patrick Gailey, AFP. Can I ask a bit more about the physical properties of the core itself? How big will it be? How heavy? How far down do you have to go? How do you transport it and stop it melting?
Can I answer for that? Okay, ice core will come, as you see, in cylinders, which have more or less the diameter of 10 centimeters. Altogether, you see the green tube there is, in this case, is probably 2 meters, but in our case, it will be 4 meters. So we have to go deep of about 2.7 kilometers, so which is a long way down. It will be stored initially on site. It will be cutted on site longitudinally at the first, and part of the ice at the end of the season will be brought back. Of course, we have to maintain the cold chain from site to EU labs, and that's not easy. We also plan to bring at least a good part of the ice at minus 50 degrees. That because we want to preserve some information, and especially on gases, especially when we have to date, because we have new method for absolute dating the deepest part of the ice, and that's part of the new scientific and technological advances that we are doing, and that's what we want to keep. It will then arrive in all the ice will be brought back, even the upper part, because we want to test our analytical tools. And then the deepest part of the ice, when it will arrive in hopefully 24, and then if we have anyway a backup season in 24-25, it will it will go on a lab where we do all the analysis together in a continuous way. So the idea is to melt the ice slowly and then distribute to several instruments, which will give us the temperature profile, because we will look at proxy for the temperature, we will look at the chemistry contents, we will look at the gas content and the dust content, and so on and so forth. So it's a long process to keep the ice cold from the beginning to the very end, to the analysis.
Thank you.
Sorry, another question just for Catherine and Carlo probably. I just wanted to know, you talked a little bit about how you're as sure as you can be. Can you put like a percentage, of likelihood of the, actually going back as far as as you point out, it starts to get a bit blurry down further down, and also could you maybe talk a bit, Carlo, about in terms of the, it's presumably a huge technical challenge. You mentioned the conditions you're working in. What can go wrong when you're doing the actual drilling?
Do you want to start first?
Start first.
There are many things that can go wrong in a big expedition like that. First of all, we have no fuel in the field, and that might happen because we have to buy fuel in Australia. Then the fuel has to travel to Antarctica, and it's not easy how to transport it. A few times it happened that in Dumont-D'Urville there was so much sea ice that the ship has to stand quite far away from the station. So you consume more fuel to transport it into the station than when you can really use in the end. Then, of course, let's suppose that everything is fine. We start drilling. There are many things that can go wrong because you are drilling in a very, very low temperature. Those equipment might be quite delicate. It happens already, even in that area in Dome C, that the ice drill gets stuck during the perforation. So you have a chance sometime to retrieve it and to get stuck into the hole. So at that time, I remember it was 700 meters or something like that. Maybe, Jérôme, you remember better than me.
I was there.
780 meters. So we might have chance to retrieve it, but we can't continue on the same hole, so we have to change the hole, and that's, of course, is at least in that case, it was more than one season completely lost. And then consider again that we will live in a very harsh environment at a very low temperature, and having 14 people alone in the field, it makes something very, very challenging. Every very little things that in Vienna is nothing. I mean, there is amplified by orders and orders of magnitude. So
yeah, and we have a very large chance to get 1.5 million years. I would say more than 90% chance, or even more, because it's by far there are layers that it's really very likely, but we are not sure that they are well stratified, and for this it's difficult to assess, and especially the question is that it is a very local thing. So at the beginning of next season, a new radar from AVI will go and do additional measurement to check whether the site we have selected should be moved by a few hundred meters just to get exactly the place where it seems the best, if the radar that new radar can see down to the bottom layers.
Maybe I can add or just add to that. So, as Carlo mentioned, this whole thing, our Beyond EPICA Oldest Ice initiative, is part of the International Partnership for Ice Core Sciences, which is a global endeavor. Now you have these two pencils, our oldest ice pencils, and they are identical. Now I give one to you, and I take one, and we meet again in 5 years, and then we see what they look like. We cannot be sure they look the same, but that's why IPICS actually has the idea to drill 2 ice cores. And that's also why we not only investigated one place right from the beginning, but also investigated another place, the Dome Fuji area, where there's a Japanese station. And that's also why we were supported in the whole pre-site survey by Australia, by the US, why we have collaborations with Russia and also with China. Because in the end, our interpretation of the ice core relies on something which is comparable, so that you can see the signal you have in one ice core, is that the same in the other one? Then we are really sure. And if it is different, we have to ask, why is it different? What are the differences at these 2 places? Is there deformation? Is there different flow information in the ice core? Is there different distortion? So that's kind of our backup.
Jonathan Amos, BBC. Barbara, can you speak more to the cause of the transition? You say a steady decline in CO2 then results in changes in the ice on Earth. What can you just explain that again? The link to
there are some
second.
records, for example, of from the marine records that show us that during this period we have an increasing amount of dust. And this increasing amount of dust can, you know, that there will have an effect on the carbon dioxide in the atmosphere, because we have a drawing down of CO2 or carbon dioxide due to the fertilization effect of the dust in the ocean, and this has been shown we can have a higher amplitude of the carbon dioxide in interglacial variability during this transition toward the 100 kilo year. So this decrease will have an effect also on the ice sheet sensitivity to the climate forcing that is due to the carbon dioxide also. But perhaps the 2 hypotheses, both the decreasing of the carbon dioxide and the regolith hypothesis, are going together perhaps. So there are both effects that can have an effect on a more difficult way to deglaciate the ice sheet after the mid-Pleistocene transition.
Just explain this regolith hypothesis again.
This regolith, the regolith is a sediment that comes from the weathering of the rocks, and as we progress during the Pleistocene glaciation, we remove this regolith through the glacial erosion, and so the interface between the ice sheet and the bedrock changed, and this difference in the ice sheet interface has an effect on the ice thickness and also on the areal extent of the ice sheet of the northern hemisphere ice sheet of the Laurentide ice sheet.
So it gets harder over time for the ice sheet in the north to grow.
Yeah, to deglaciate.
To deglaciate. Right.
So okay. It begins more thick and more extent.
Okay, and so that suggests there's a tipping point at about 900,000 years.
Yes, we could also think about this, yes.
Are there any further questions from the journalists here in the room or those watching live? No? In that case, we'll finish here. You are welcome to approach our speakers. We have interview rooms available that you can book at the info desk. And I'll thank very much for your speakers for your time. And I would like also to thank to the Avi and Bas media team for their help. Our next press conference is at 10:30 on new plastics research. Thank you all very much for coming.